Good day, good evening, good morning. Welcome to the last TDS webinar of this year. So it's my pleasure to introduce Pierdomenico Pepe, who's full professor at the University of L'Aquila in Italy. So Pierdomenico, I don't need an introduction is needed. He's a top expert in nonlinear control, time delay systems with seminal theoretical contributions, but also with applications in biomedical, electrical, and chemical engineering. Impressive is also the service to the community. So he served in many IPCs and organizing committees. Among others, he was lead organizer of the TDS workshop in L'Aquila in 2006. And he also served in editorial boards of many top journals in our field. He also has edited several books, volumes, and special issues on time delay systems. So we're very happy, Pierdomenico, that you accepted to give a talk, and we're looking forward to it. So if you're ready, you can start. You have the floor.
Thank you very much, Wim, for your nice presentation. The talk deals with the guarantees which can be given to a closed-loop system when the controller is designed in continuous time in general, and then it is implemented by sampling and holding. And the problem is addressed for systems described by retarded functional differential equations. The outline is as follows. I will introduce retarded nonlinear systems, then I will give some results for globally Lipschitz systems. Then I will introduce the notion of stabilization in the sample and hold sense. I will deal with implementation issues. I will deal with discontinuous feedback as well. And I will give a glimpse to the case with time-varying delays, and I will draw conclusions and future developments. First of all, I would like to highlight these papers, which have been very inspiring for the activity and for the results which have been achieved and are going to be presented in this talk. First, the papers by Clark et al. And on stabilization in the sample and on sense, and this paper of Wei Lin about when it is possible to achieve semi-global asymptotic stability under sampling for a nonlinear system. About sample data control system described by retarded functional differential equation, there are a lot of works, especially in the last 10 years, I would say 10-15 years, and there are papers which consider classes of systems and particular feedbacks and so on. I'm going to show mainly the results which are present in these papers here and in a paper with Emilia Friedman. Let us give some notation, some standard notation. Okay, for a positive real H and integer n, I will denote BHN as the ball of the origin with the radius h, where here x is the standard, the norm of x is the standard Euclidean one. And C is the space of continuous functions mapping minus delta 0 into Rn. And for phi in C, the supremum norm is defined in this way. This is the supremum of the Euclidean norm over theta in minus delta 0. And this is the state space of the systems that I'm going to consider. And for a positive real H, CH is the ball of the origin with the radius h, and the functions in C with the supremum norm smaller than h. And here I set also another space which is very important for a positive real Q. W1 infinity Q is the set of the absolutely continuous functions such that the essential derivative has norm less than or equal to Q. In the following, this Q could be arbitrary, but it must exist for our results. What are systems described by retarded function differential equations? As well known, it is an equation written in this form, x dot of t equal to f of x sub t of t, where x of t is in Rn and delta is a positive real, the maximum involved time delay, and x sub t belongs to C is defined in this standard form, which is very well known. By this notation, it is possible to consider here an arbitrary number of arbitrary time delays of discrete type and also distributed time delays. It is very general. And U is the input, which will take the place of the control law. Anyway, in general, it is a Lebesgue measurable local essentially bounded signal, and M is a positive integer, and F is a map from C times Rm to Rn, Lipschitz unbounded sets. So we are in a situation which is rather general, as we assume the Lipschitz of F, the Lipschitz property of F only on bounded sets. And we assume f of 0, 0 equal to 0, so the trivial solution 0 is a solution. We give here some standard definition for which are very well known. Here the global asymptotic stability is meant in the uniform sense. Anyway, we say the system is zero gas if there exists a function beta of class KL such that this inequality holds. Class KL means that I am decreasing to 0 in the second argument, and in the first argument I'm increasing. But when the initial state is fixed, this is a function which goes to 0. And zero Jess, globally exponentially stable, of course, if this inequality here holds, and the exponentially stable in the sense of local exponentially stable when there is a ball of the origin, so a positive real h and positive real m and lambda, such that this inequality holds whenever the initial state belongs to ch. And finally, this is very interesting, rather novel definition of zero Gales, which was given by Wei Lin in 2020, and it is about the property that systems are both globally asymptotically stable and zero S, that is locally exponentially stable. This is the definition of partition, as we are dealing with sample data control. Of course, we have to define a partition. A partition is the sequence of the sampling times, which in general is not uniform. So we have an initial sampling time t0, which is equal to 0. And of course, the sequence goes to plus infinity as I goes to plus infinity. And the diameter is the supremum of the difference between two sampling instant. And the dwell time is denoted as the infimum of two sampling time. Of course, it could be 0. But we assume that it is not 0, and actually we introduce this notion for any a in 0, 1, and delta positive real. Pi a delta is any partition pi with a delta smaller than the dwell of pi, smaller than diameter of pi, smaller than delta. It means that the ti plus 1 minus ti is always bigger than a percentage of the maximum sampling period. That is always bigger than a delta. A is in 0, 1. When a is equal to 1, it means that the dwell time and the diameter are equal. That is, we have a uniform sampling. That is, Tj is equal to j delta. This is the first result that we are going to give, and it is about systems which are globally Lipschitz and for which there exists a feedback K which is still globally Lipschitz, and such that the RFID system in closed loop with the control law U of t equal to K of xt is zero Jess. So here the assumptions are F is globally Lipschitz, the feedback is globally Lipschitz, the closed loop system in continuous time is globally exponentially stable. where under this very important conditions, anyway, we obtain an important result. That is, for any A in 0, 1, there exist positive reals delta max, m, and lambda, such that for any partition with delta less than delta max, the solution of the RFID system corresponding to any initial state x0 and to the sample data feedback control law UOT equal to k of xtj, that is, we make the sampling and then we apply the zero-order holding device. So in the interval tj plus 1, we freeze the input, which is piecewise constant because it is equal to k of x sub tj. The solution exists always and furthermore satisfies this inequality. So we have hard conditions, but as well the result is significant because it is a global one, and this m and lambda can be fixed once for all the initial state. So a global result. Of course, a consequence of this is that there is the consequence for linear systems, because clearly linear systems are globally Lipschitz. So, for instance, if I have a system of this type with discrete delays, an arbitrary number, non-commensurate as I like, and if I assume that there exists a state feedback like this, so for a suitable matrix K and UOT equal to this feedback is globally exponentially stable, then I'm sure then that the global exponential stability property is preserved under sampling, provided sampling is suitably fast. And of course, for the linear case, there is a huge literature. I cite here two most recent books on the topic, one from Friedman and one from Michiels and Niculescu. Now let us go to the case in which I remove the assumption of F Lipschitz unbounded set, and I give the definition of stabilizer in the sample and hold sense, which was given by Clark et al. And was some adapted to retarded system in this paper of mine in SICON 2014. A locally bounded feedback K, which goes from C to Rm. C is the state space, so the feedback is always from the state of the system, so from x sub t, and in general it involves time delays, continuous or not, is a stabilizer in the sample and hold sense for the retarded functional differential equation system that I gave at the beginning, if for every positive reals Q small r capital R, where Q is the maximal derivative of the initial state in norm, R is an arbitrary positive number and also capital R, but this inequality holds here, and A is indicates the percentage of the maximal sampling period in the dwell time. There exists a delta max, which is the maximum sampling period, a positive real t, which is the uniform settling time, and a positive real e uniform overshoot, such that for any partition with delta smaller than delta max, and for any initial state which is in this ball, the solution corresponding to x0 and to the sample data feedback control law UOT equal to k x sub tj, that is the piecewise constant control law by sampling and holding, exists and furthermore satisfies this, that is, for any t greater than 0, the solution is in this CA, that is in the ball of radius E. That's why E is called overshoot. And xt belongs to CR for any t greater than capital T. That's why capital T is called settling time. What is important to notice is that this capital R is fixed arbitrarily, and also the final target ball is fixed arbitrarily, and then when I have fixed them, I can, for any initial state in the ball of radius capital R, all the solutions are driven into the small ball after a setting time which is uniform for all the solutions, and this for a suitable small sampling period. So from an engineering point of view, this definition is very nice because it allows to reach in a fixed settling time for a given set of initial states, which are the ones which are needed to reach the precision that we need. But here there is the convergence to zero is not given. This is the convergence in a suitable small ball, final target ball of the origin. What happens with the Lipschitz unbounded set zero gas systems? Well, with this definition, if we have a feedback K which goes from C to Rm Lipschitz unbounded sets, such that the retarded function differential equation system in closed loop with the control law, again, UT equal to Kxt is zero gas. Under this assumption, so when we have the function f is no more globally Lipschitz, but just Lipschitz unbounded set, and as well we have a feedback K Lipschitz unbounded set, such that the closed loop system is globally asymptotically stable when applied in continuous time, then the feedback K is a stabilizer in the sample and hold sense. That is, when we apply this feedback by sampling and holding, like in this equality here, UT equal to K of xtj, we always obtain the system that the feedback is a stabilizer in the sample and hold sense. That is, drives solution starting in the ball of radius capital R into the ball, target ball of radius small r, with the unique settling time and with the unique overshoot. This is the situation where we consider the same conditions as before, but now we assume that the closed loop system in continuous time is zero gas. This is the difference with respect to before. Before we assumed zero gas. Now we assume that we have found a feedback K of x sub t, so as well can involve delays and so on. And but in this case, we assume that the closed loop continuous time system is globally asymptotically stable and locally exponentially stable. Then, of course, in this case, the feedback K is a stabilizer in the sample and hold sense. But on the other hand, we have another result that is, in this case, as in the original paper by Wei Lin, we obtain that there exists a sufficiently small delta max such that the solution of a sample data closed loop system with delta smaller than delta max satisfies this limit. That is, the supremum of the solutions for all initial state phi, which belongs to a radius, a ball of the origin of radius r, and always with a suitable derivative in norm of the initial state, is equal to zero. So we have a uniform convergence to zero, uniform with respect to bounded set given by this capital R. Let us consider now a typical problem in implementation. What is a typical problem in implementation is that when the feedback K of xtj is considered, in general it involves time delays. That is, for instance, x of tj minus tau is involved for some tau in minus delta 0. So, of course, what is sampled is x of ti, no? the internal variable, which is at time ti, And so it may well happen that since xti is sampled for j minus p, j minus p plus 1 until j, until I arrive to x of tj, and they are saved in the memory buffer. If the feedback k involves x of tj minus tau with the tau some particular delay, it may well happen that it is not available in the memory buffer. So we may have a disposal only of xtj minus tau1 and xtj minus tau2, but tau1 bigger than tau, bigger than tau2. So if multiple non-commensurate delays are involved, then for sure at least one delay term is not available in the memory buffer. So we need a further approximation, and the approximation is made by means of splines. That is, we consider first order linear approximation. That is, when we have two samples, we unify them linearly, and but we have to pay attention that the sampling times, of course, they are not uniform. So the distance between two sampling time cannot be, can well be not uniform, and therefore the problem is overcome in this way. We define a buffer of times which mimic the sampling times, such that the first one is always equal to 0, and it mimics the current sampling time. And then the other, they are the past sampling time, which have a distance from this one, depending on the time elapsed between two sampling times. And so we have W0 equal to 0. The difference from the first and the last must be greater than delta, because delta is the maximum involved time delay. And the difference between two is smaller than the maximal sampling period and bigger than the dwell time, A delta. And then we define this operator, which goes from the buffer of sample data internal variables, that is this zeta0, zeta1, zeta-l, mimic x of ti, x of ti minus 1, and so on, which are put in correspondence with the set of times, that is of sampling times. And then this operator, given the set of sampling times and the set, the buffer of the internal variables, the sampled internal variables, computes the value at any tau in minus delta 0 by this interpolation, this simple interpolation between the sample data. And where is the small integer such that tau is in the middle of two values of this vector wj, because tau, these are always terms in the past, so from 0 to minus delta, and also tau is minus delta 0 as a value which indicates some delay which is involved in the feedback. So when I apply this methodology, what is the approximated sample data state feedback? Well, the feedback becomes the state feedback A, but applied to this interpolation, so it is no more x sub tj, but it is this interpolation, which depends on the buffer of sample data internal variables and the buffer of the sampling times. And of course, this is piecewise constant, as usual in the sample data control law. And what is the initialization? The initialization is simply the initial sampling time is 0, and then these are negative terms, which are the sampling times for the initial states. This is the buffer, the initial buffer, which is given by x0 of 0, x0 of t minus 1. Okay, it involves the initial state at different times. Then, what is at every j? What happens? There is the buffer of sample data is incremented by entering the current x of tj and losing the last one. So the last one exit, all the other x of tj minus 1 are put back in the buffer, and the buffer of times is is as well updated, maintaining always 0, the first one, and the other one, the last one is lost, the last sampling time is lost. The other one are put back in the buffer, and what happens that they are shifted of this term, that is the time elapsed between the most recent sampling time. So they go back because, of course, this is the time that has recently elapsed, so the value of the other sampling times has to go back of this time. By this way, it is very easy to implement this feedback, and what I need is always to know the difference between the most recent sampling time. Of course, this is a further approximation, and so one has to see what happens when one apply this kind of approximation, and furthermore the sampling and holding. So let us consider first the local result. When here I have a function f, which goes from c times Rm to Rn, and we say that it is Frechet differentiable if there exists bound linear operator L and matrix B, such that this limit exists. So it is the definition of Frechet derivative. We assume that the system is Frechet differentiable at 0, 0, and so we consider the linearized system, which is given in this form. Now, for this linearized system of the original system, nonlinear one, of course, there is a lot of literature for finding a stabilizing feedback for the linearized system. And so let there exist a linear bounded operator such that the linear system, this one, is 0s, which of course corresponds also to global exponential stability. This is a time invariant linear system. And now fix A in 0, 1, A is always the percentage of the diameter in the dual time, and Q be a positive real arbitrarily fixed. Then there exists positive real HM lambda and delta max, such that for any partition, pi a delta with delta smaller than delta max, and for any x0 in ch times w1 infinity q, the corresponding solution xot of the RFD system in closed loop with the piecewise constant control law, which is the one approximated, the approximated one, so fully implementable, exists for all t in R plus and satisfies this inequality. That is, I can say that whenever I have a feedback for the linearized system in continuous time, then I apply it by sampling and holding and by approximation of the state by means of the buffer of sample data internal variables and the buffer of the sampling instant, that is in this way by this feedback A of pla delta of Bs of j and beta of j. What happens is that the local exponential stability is preserved. Let us give a look now to the discontinuous feedback, and also in order to give some methodologies for proposing a feedback which may work for sample data. Not until now we have assumed that we have it. So let us consider this definition. We have a couple phi1, phi2 belonging to C times C, set the pi needle couple if the equality phi1 of 0 is equal to phi2 of 0. And we say that a map K is said to be uniformly in time Lipschitz by pi needles couple on bounded set of C if for any positive real Q there exists a positive real LQ, such that for any t in R plus and for any pi needles couple phi1, phi2, this inequality holds. That is, roughly speaking, we say that K is uniformly in time Lipschitz by pi needle couples if it satisfies the Lipschitz inequality on a given bounded set, on every given bounded set with a suitable constant LQ. but only if phi1 and phi2 are equal at 0. This is needed because in the spline approximation, what happens is that the value of the spline at 0, the value of the approximation at 0 at the value of the x sub tj at 0 are the same because they coincide with the x of tj, that is the sample data at current time tj. Well, I define here a function v which is said to be smoothly separable if there exists a smooth function v1 and the Lipschitz unbounded set function v2 and function bi of class k infinite such that this inequality holds. That is, I can split v in the sum of two terms. v2 must be non-negative and v1 must satisfy these standard inequalities. Of course, when I cannot have subtract, for instance, but I have also to guarantee that this V2 is non-negative, and I must satisfy this inequality here. And let's say what is the definition of a control Lyapunov-Krasovsky functional. So a control Lyapunov-Krasovsky function, I take it in this set, in the previous set of smoothly separable functional, such that this inequality holds. Now V is the sum, and this inequality holds whenever phi of 0 is different from 0. This is a standard definition of control Lyapunov function as is adapted to nonlinear retarded systems, that is for systems, in this case described by retarded function differential equation. This is the derivative which does not compute, does not involve the solution at all, so this condition can be checked for any phi and u, and this definition was given by Driver in 1962. Now, we say that a locally bounded map K, which goes from C to Rm, continuous or not, is said to be a steepest descent feedback induced by control Lyapunov-Krasovsky functional V if the following condition holds. There exist positive reals eta and nu and a smooth function P of class K infinity such that for any phi this inequality holds. Okay, this is the driver derivative of the whole functional V, and you can see this as a perturbation which is can be read small in some sense because eta can be arbitrarily small, nu can be arbitrarily small, and this function P, which is of class K infinite, can be chosen very slowly increasing. Anyway, this is a condition which allows us to apply the results about the stabilization in the sample and all sense that I will show you later. And if this inequality holds in CH, that is in a ball of the origin for some positive real H, then K is said to be a local steepest descent feedback. Well, let us assume that there exists a positive real Q such that the initial condition x0 belongs always to this set. And we assume that there exists a control Lyapunov-Krasovsky functional V and an induced steepest descent feedback K, continuous or not. And the map phi to d plus v2 phi u is Lipschitz unbounded set. Notice that K can be an arbitrary feedback. So if I go back to this condition, I assume to have a control Lyapunov-Krasovsky function, and I have to try to find a feedback K also discontinuous, whatever, such that this inequality holds. Well, there is this theorem that the steepest descent feedback K, that is the feedback K that satisfies this inequality, is a stabilizer in the sample and all sense. So when I applied it in this way as K of x tj, I get the stabilization in the sample and all sense, that is, I recall deriving solutions from a ball of capital R, of radius capital R, to a ball of radius small r that I fix arbitrarily. And if K is a Lipschitz unbounded set by pine needle couples, that is, it is allowed to be discontinuous, but it must be Lipschitz on pine needle couples. then is a stabilizer in the sample and all sense by spline approximation of the state. That is, I can use the feedback that I showed you by means of buffers of sample data and buffer of sampling times. Of course, I can always apply k of x tj if for instance, if I have delays which are, if it is possible to choose the sampling period, which is the delay is equal to multiple of the sampling period, of course I have no problem. Otherwise, if I apply OT equal to k of xtj, there are implicit some approximation which must be taken. But anyway, if I make the interpolation and I have the property that the K is Lipschitz unbounded set by pan-Nieder's couples, then I am guaranteed that the stabilization in the sample and all sense by spline approximation of the state holds. So if K is a local steepest descent feedback, then it is a local stabilizer in the sample and all sense by spline approximation of the state. So a local stabilizer, which has the same definition, but now I have a local set, a fixed set where I have to choose the initial state. Of course, provided that this feedback K is Lipschitz on one bounded set by pan-Nieder's couples. This is an example from sliding mode control, in which is taken from, it is a motivation example in the book of Khalil, in the case without delays. And so we have these two variables, H and G are uncertain maps, Lipschitz unbounded subsets of C. H of 0 is equal to 0, and X0 is in this W1 empty Q, where Q, I recall, is the maximal norm of the derivative of the initial state. Which is assumed to be absolutely continuous. And U of t in R is the control input. Well, if I assume as usual that there exists a positive real G0 such that G of phi is bigger than G0, and for chosen positive real A1, there exists a function ρ, Lipschitz unbounded set, such that for all phi, I have this inequality here, which is standard in sliding mode control for this significant example. And so I have V of phi. V of phi is decided in this way, where this is the sliding surface, and V in this form, and the feedback, this is the standard sliding mode control for this example. K0 is a positive real control tuning parameter. Then this Lyapunov function V, functional, but actually it depends only on phi of 0, as you can see. It is a control Lyapunov-Krasovsky functional, and K is an induced steepest descent feedback. That is, it satisfies that inequality that I showed you before. That is this one. And so what happens, and furthermore, it is Lipschitz unbounded sets, so there is no problem at all to say that we can apply the theorem. So the feedback K is a stabilizer in the sample and all set by spline approximation. One should notice that this feedback K is discontinuous as standard in sliding mode control, but it is Lipschitz unbounded set by pan-Nieder's couples, because if I pick phi and psi, which are equal at 0, the term sine of 1 phi 1 of 0, etc., and sine of I1 psi 1 of 0, etc., they eliminate each other when I make the Lipschitz inequality, and rho phi is chosen to be Lipschitz unbounded set. So this is a discontinuous feedback, but it is Lipschitz by pan-Nieder couples, and so the problem of the discontinuity is overcome. I can apply it by the feedback approximated by the splines that I have shown before, and drives every set of initial state in capital R in the whole solution are driven into the small ball of arbitrarily chosen radius small r. Okay, these simulations are performed with this H and G, where B1 and B2 are uncertain parameters. Delta is a known constant, and we choose for simulation A1 equal to 1. This is rho phi, which of course does not involve these unknown parameters, and with this value of the initial state, the delay, and so on, we have here uniform sampling, but as you can see, the spline approximation is always necessary because delta is not a multiple of the sampling period. So of course there is value of in the feedback. Some terms are not available for making this feedback which involves rho in evaluated in minus delta, because it is not available in the buffer, so we have to use the interpolation. Okay, these are the behavior which shows a good performance of the controller with delta equal to 0.6. Here we have a continuous stir tank reactor. There is a recirculation, so CAOT, the reactant concentration, TROT is the reactor temperature, and there is a delay due to the recirculation, which can be seen in the model. It is nonlinear. Of course, I will not explain the parameters here, but just to give an example, the manipulated input is the jacket temperature, TJOT, and if we consider the variables as the deviation from the operating point, which are obtained by a suitable fixed reaction conversion, we obtain the system tree here, which is given in this form, where F and G are readily defined by the original model equation. Then a feedback is this one. A feedback is for K is this one, which can be found by standard tools of differential geometry. And the feedback K is a local steepest descent feedback induced by this control-Lyapunov-Krasovsky functional. So it is a local steepest descent feedback, and so we can apply it because we know that it is a local stabilizer in the sample indoor sense by spline approximation of the state. And we obtain these functions, these plots here about the reactor concentration, the deviation from 0, so it goes to 0. Also the reactor temperature goes to 0, that is we go to the operating point when delta equal to 300 and equal to 0.1. So the sampling period goes from 30 seconds to 300 seconds. And actually this is the control signal, and as you can see, we have a different sampling period because they go between 30 and 300. Let us give now a glimpse to the case of time-varying delays. That is, we have the situation in which F depends also on time, not only on x sub t, but also on time. But this dependence is due only to time-varying delays. So, and we assume that F is a continuous map, uniformly in time Lipschitz on bounded set of C times Rn, uniformly in time. And this happens when we have time-varying delays, and in general. So we have these are conditions, technical conditions. Okay, this is Ft of 0, 0 is equal to 0, and this condition here says that for any positive reals Hi, I equal to 1, 2, 3, 4, there exists a positive real eta such that for any T1, T2 in R plus satisfying T1 minus T2 less than H1, and for any U in the ball of radius H2, for any phi in the ball of radius H3, but phi which satisfies this inequality. So whenever I have a phi which satisfies this inequality, so for instance, whenever phi is an absolutely continuous function with bounded derivative, whenever this happens, then I must have this inequality here. So for instance, this inequality can hold when I have F Lipschitz on bounded sets, and the time delay is globally Lipschitz, and for instance, discrete time delays. In that case, and the function phi is, for instance, absolutely continuous with essentially bounded derivative, because in that case this holds, and the delays globally Lipschitz yield the last inequality. Actually, in the third point, I write that the depends of the map F on the time argument is due exclusively to the involved time-varying time delay signals, and any time delay signal is bounded by delta involved in the dynamics on system 4 is globally Lipschitz. So I assume the globally Lipschitz property of the time delays. Well, now we can define the analogues of the control-Lyapunov-Krasovsky functional as control-Lyapunov-Razumikin function. It was introduced by Jankovic in 2001. And what is a control-Lyapunov-Razumikin function? It's a function which has these properties, lower bounded and upper bounded by class K empty function, and satisfies whenever the Razumikin condition holds, that is, whenever rho v of phi of 0 is greater than this, when rho of s is bigger than s, then I have the infimum with respect to u in Rm of this derivative is less than 0, where this is the unidirectional upper right-hand derivative defined as usual in this way. And what is important, so there must exist a u such that this is negative. This is negative. So we assume to have a control-Lyapunov-Razumikin function. And now we give the definition of a locally bounded map K, steepest descent feedback induced by Razumikin functions. So a locally bounded map K, which goes from R plus times C to Rm, continuous or not, is said to be a steepest descent feedback induced by control-Lyapunov-Razumikin function V if there exists a positive real nu, a function alpha of class K, a locally Lipschitz function gamma of class K with alpha minus gamma of class K, such that for any t in R plus and for any phi in C, the inequality holds this one. This inequality, which resembles the kind of Alan-I inequality, but in nonlinear term. No, I have the term alpha and gamma, which are nonlinear. Well, when I have this, the derivative d plus v, that is the previous one, when at the place of u, I set k of t phi, when I get this, satisfying this inequality, when I get this derivative here, when u is equal to k of t phi, if I get this inequality, and look that k is can be continuous or not, there is no, nothing is fixed about the regularity of the feedback K, but I have to satisfy this inequality here. D plus V is computed without involving the solution, and so assume now that there exists a positive real Q such that initial state is as usual in this set, and there exists a control-Lyapunov-Razumikin function V and a uniformly in time locally bound induced steepest descent feedback K, continuous or not, uniformly in time Lipschitz by pan-needle-Scapels unbounded subset of C. That is, I assume that the feedback K, continuous or not, is Lipschitz but on pine needle-Scapels. There are results also without giving this condition, but I give now the result when the spline approximation is used. So assume that the feedback K is uniformly in time Lipschitz by pan-needle-Scapels unbounded subset of C. And so we have this theorem that the steepest descent feedback K is a stabilizer in the Sembrandorf sense for the Razumikin, the retarded function differential equation time varying system by a spline approximation of the state. That is, the feedback now is this one, and it is a feedback which consider the time K of Tj, but this feedback, the Tj involves the delays tau of Tj by which I can go to consider inside this buffer when which are the terms that I have to take. So now this feedback is of course given Tj. If the delays are time varying, they are involved different time delays at time Tj, Tj plus 1, and so on. Well, this is an example. This is a benchmark which is studied in an example which is studied in many papers. It was introduced with the delays constant, tau1, tau2 equal to delta. This is considered with the time varying delays. Tau1 is unknown. Well, this feedback, which was found by Jankovic in constant delay, and it is proved it works also with time varying delay. This feedback is uniformly in time Lipschitz unbounded set, and so also by Pan-Needle couples, and induced by this Razumikin function. So case is stabilized in the sample and all sense by spline approximation of the state. That is, I can apply this by means of PL delta as an operator, and on the buffer, on the finite buffer of sample data and sampling times. This is another example taken from Khalil in the delay-free case, and I introduced some delays. And in this case, well, the interest of this example is because it shows how the discontinuities can be managed, and the time delay system tau t and the parameters are unknown, but we assume to know their bounds. So we have this situation where delta is known and also the upper bounds. We have the sliding surface, this one, a1 x1 plus x2, with a1 a positive real greater than theta 1 over line, the bound for theta 1. And what happens is that when I choose this Razumikin function, and I get this feedback, which is again discontinuous because it is designed with using the sign of S of phi of 0, so it is discontinuous in this set. And remember that phi is a set of function. Phi is a function, so it is discontinuous whenever it happens that S of psi of 0 equal to 0. And the feedback case is steepest descent feedback induced by V, Lipschitz unbounded set by Pan-Needle couples. Actually, as I showed for another example before, this term disappears in the Lipschitz inequality, so I have no problem to say that it is Lipschitz unbounded set by Pan-Needle couples. So K is a stabilizer in the sample and all sense by spline approximation of the state. That is, initial state in a bounded set, all the solutions starting in a bounded set arbitrarily fixed are driven to a small set, a small neighbor of the origin whose radius is fixed arbitrarily, and in a uniform setting time and with a uniform overshoot, provided that the sampling time is sufficiently small. Results are available by the methodology that I have shown also for dynamic output feedback, and there are this paper on sample data emulation of dynamic output feedback controllers and on automatic, and this other paper on transaction automatic control for a new approach to the design of sample data dynamic output feedback stabilizers by means of control-Lyapunov Krasovsky functionals. And there is this paper, this last paper here, which is fully devoted to the control of the glucose insulin system by the methodology here provided. And here there are also further results the audience could be interested about the event-based sample data stabilization by the methodologies that I've shown before. And the interest is mainly on the fact that the monitor of the output is not necessary in continuous time, but that actually only at sampling instance. And work in progress. Well, a very interesting research line is to find stability guarantees under sampling for nonlinear system affected by time delays in state and input-output channels when continuous time predictors are involved. The case of time-varying time delays is as well a challenging topic, and asymptotic stability guarantees under sampling have mostly to be established, that is, the solution going to zero. Exponential stability guarantees under global Lipschitz property will be presented by Caiazzo et al. At next CDC. Another interesting topic is the stabilization in the sample and all sense of system described by the retarded function differential equation with the discontinuous right-hand side in a Filipov-Krasowski solution framework. And finally, the stability guarantees under sampling for switching retarded systems is also a very interesting research line. Thank you very much for your attention.
Yes, thank you very much, Pierdomenico, for this nice talk, which is deep and broad at the same time.